Hey everybody, this is Larry. This is me going Q2 of the bi-weekly contest 142. Find Subtree sizes after changes. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. I think this one, honestly, it's I don't think this is a tricky algorithmic problem because I think they tell you exactly what to do, frankly. But the implementation can be really tricky, and if you're not careful, you can certainly just be wrong, but do things in n square, right? Or something like this, which may be too slow. So I think the first thing that I would think about with problems like this is, well, one is that it's a tree problem, and one observation is that the reason why they kind of structured it as in a functional graph or a parents-based kind of way instead of a left-right node is, well, so that you can have multiple children for each node, right? And basically all this problem is asking is that you're trying to basically merge up to the previous character that the previous same character that you've seen. So you have to just be careful about how to interpret the problem in general, right? And that's the first thing that you notice. And I think that part I don't think is that tricky. They tell you about it in a very precise way, so you do have to decode a little bit what they mean, but it is relatively precise, and that's fine. And then you just basically if it exists, then you remove it with its parent and then just connect it with the new one. So there's really only one thing or two things to do, right? Just remove and make the new parent. And how do you do how I would think about it is there are two things that every node. What do I care about? Well, two things, right? One is the ancestor that gives you the node that you care about, and then the other is the ancestor that you care about and the parent, because, well, you just need to know the parent, right? And I think there are two ways to think about this, right? Or two ways to attack this problem. I don't know if you can do it both ways, but one is kind of going from the leaf up, and then the other is just going from the root down, right? The way that I did it is through the root down, but you can also do it from the leaf up by kind of just like basically doing everything I did backwards by you can count the number of. We could talk about the leaf up situation later, but I think you can certainly do it that way. I think it's not that bad. You just basically propagate things up and then removing children from each other. But yeah, one key thing to note is that, and this is kind of a thing that happens on Leetcode, but happens on code forces and competitive programming in general, is the constraints, right? But I mean the first part I kind of just add in because it's obvious, but still n is 10 to the 5th. Again, that means no n squared, right? You have to do something in O of n time. The second thing is that and this is just a radical tree stuff. It's just trying to tell you that, hey, look, we promise it's a good tree, so you probably have to kind of focus on it a little bit. But sometimes they do trick you by having like edge cases that are weird, but for this problem they do not. The second is that, again, constraints, right? Is that it can only be of 26 lowercase English letters, right? And that makes it a little bit. It gives, well, there's just more possibilities because then now this can be a thing that you take advantage of, and that is in fact what I did. So what I intended to do was basically have two passes, right? One pass is to do what they tell you, and then the second pass is just to count up the nodes. That's how I kind of structured in my head, and that's how I have these functions, even though I wrote them in a really dubious way. But yeah, okay, but let's go over the code then, right? The code, first of all, I just convert this from the parents list thing to basically to one that's based on a node and then its children, so we don't have to go the other way. And then here, as we said, for each node we only care about the parent, but also what I call a last seen thing, right? And what I mean by last seen is that last seen is last seen sub C is the node that with last seen C in, right? And what I mean by that is just that it'll be the node that's closest to the current node that we've last seen a certain character. Keeping in mind that also when you look at this code, I do actually translate it from A to Z to 0 to 25 just to make things a little bit easier for me. You don't have to do it, but I don't know, maybe you do, I don't know. But yeah, so then now, despite the dubiously named thing, but this will do the operation of removing it. Yeah, so basically this is saying that, okay, so this is the current value of the current node, and if the last seen of it is not none, then we do the thing about removing the parent, and we also update it, because the parent directly we don't, we have to remove it, and then we update it to the last node seen. Keeping in mind that if parent is equal to last seen, then this is a no-op. It's an expensive no-op, but it's effectively a no-op, or maybe a spin-op, if you will, spin lock. But yeah. So this we figure it, and then after doing this connection, we just do it recursively. We go, okay, well, this we set this up to look at the previous last seen, so that when we update this, we can revert this later in the recursion, right? And that's basically what I mean. I guess you can make a copy of it, but the reason why we did it this way is because then now you only need one copy, and it doesn't take 26 times n space. It only takes 26 space, right? So instead of alpha times n space, which honestly gets a little bit big when it's 10 to the 5th times alpha, we are able to do backtracking with just, by manipulating it, and we pass in the pointer instead, right? Or the reference, sorry, because it's Python. But yeah. Anyway, but as a result, we have to undo the things we do. So then here we look at we set it to the previous value. After we do the recursion, we set it back, which is why we have that. And we update the node because this is what we will pass down to our children as the last node seen, right? And here we get the list of the children, and then for each of the children we just do a recursion to fix it. So you can maybe call this like a fix or a cleanup or whatever, right? And yeah, it's just for C is the number. C is the node, the new node. Node is now of the parent because you're going down to children, and we update the last seen as we talked about. So that's pretty much the idea. That's pretty much it. And then at the end, we just do a recursive loop to count all the subtree sizes, which honestly is pretty basic. It would be, it's definitely like itself a problem on Leetcode. I don't even know if it's a medium anymore, but that's, a thing that you definitely should be able to solve. Overall, I would say that this problem is trickier than usual for Q2. Oh yeah, let me go over the complexity real quick, right? So this is actually O of n times, because for each node we only look at it twice, right? Once here, and in terms of space, it's O of n because of the stack size, right? So O of n is probably fine, and yeah, plus alpha if you want to consider it that way. So pretty linear. Yeah, and alpha can actually even be like restricted by S because of the cardinality and stuff like this, right? It's just the number of unique characters, so it doesn't even have to be 26. But yeah, so for this one, I want to say for interviews and just problem solving, it's definitely tricky, especially for Q2. I think honestly, everyone or many people should have the capability to solve these problems, because all you need is an understanding of trees and nodes, which hopefully everyone on an interview level should have. But I would say that this is not a easy problem because it is not a cookie cutter problem. It's not a textbook problem. I think very often Q2s are a little bit on the easier side, not necessarily because it's hard or not because it is easy in concept, but it's just because by repetition a lot of people have solved similar problems, right? I think this is the case for Q3 for this contest, actually, in case you're curious. But you know, like if you haven't solved it before, a similar problem before, then it's gonna be hard anyway. So I don't know, but that's what I have for this one. Let me know what you think. Thanks for watching, and yeah, you could watch me solve it live during the virtual contest now. I have to do the original one, I guess. Okay. Don't know what fell, but hopefully I'll fix it later. Tree. It's a non-binary tree. It's a functional graph tree. S sub I. Man, this is a lot of reading. Maybe I am not ready for this. Alright. Find the closest. Is this? Make the one time. All nodes from. Okay, so we do it for all nodes that is not the root. Find the closest node y such that. Find. Oh man, this is such reading. Find the closest node y to know such that y is an ancestor. And, okay, so it is an ancestor and also okay, fine. If node y does not exist, do nothing. Otherwise. Okay, so yeah. And then now node 3, you want to, it removes itself. So basically it is some kind of funky thing. How do I want to think about this one? I mean, there's only 26 things, so you just keep a track of it recursively, right? I think that should be fine. Yeah, okay. Yeah, not an easy one, but it should be doable. Yeah, okay. Child, right? So yeah, okay. I mean, yeah, it's annoying, but it's fine. So we want to say, okay. Okay, yeah, I think I got it. Okay, so then now for I, P, and enumerate parent. So then the I've index, the parent is if P is not equal to -1, that's fine. Then we have children of P append I. Okay, so now we're Gucci, and then we have two depth for searches, say, or just recursive thing, right? I'm just let's just go. Don't think. Okay, and then we have the current node, and then the last scene type thing. Okay. Yeah, and then yeah, okay, and then we could just convert the S to okay. So then now we want to remove. Oh, we should have his parent. So then now, if last seen, okay, if No, it is okay. Last seen of node. No. Node is the index. Is SN of the node is not none, so we set it with none. Then that means that parent or the children of the parent, we remove node and we trying to do I need to, the recursion could be very tricky actually, because of this simultaneous thing. I don't know if there's a race condition thing. I don't think so, but we'll see. Okay, so we remove the child and then we set the last scene of SN of node dot add node children of this. Okay, and then now previous is equal to last scene of node. No, last scene of SN of node. So then we do recursion on the order child for C and children of node. We calculate the children, the node is the parent, and the new last scene, that last scene of SN of node is equal to this node. And then afterwards we want to reword it back. Right, and then now that should be good. So then we do go of 0, -1, none times 26, and then we just go to just to actually get the answer of the number of children, right? So node answer is this might have to. I wonder if we're going to get an iterate. I think that fixes it, but I hope so. Okay, anyway, so so then now answer, I'm gonna just put 0, answer of no, go to of C, and then we just return answer of no. Right? Standard recursion stuff. I have to add a +1 here, it's not quite right. Set have no append. Where am I appending? Oh, right. Oh, okay, well, that's not quite right. I mean, this isn't right anyway, I don't think, but... Updating 3. Here, we're updating 2 and 4. Something feels funky. 3, 4, and 2. Oh, I guess that's true actually. It's just that you don't really update them per se. That's why it's a little bit weird. But okay, because it's the same thing. Okay, so I think updating is right. Then why is this not right? Do I suck at the easy part? I suck at the easy part because I forgot to call it. I keep doing this actually. Okay. We'll see. Okay, good. There's some minor like implementation things there that I wasn't sure about. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, this problem, this explanation, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later. Take care. Bye-bye.